Jnanam Paramam Dheyam. Knowledge is supreme.
So, today we proceed with our discussion of representations, and hopefully today we are going to learn what is the meaning of the character tables that some of us have already used in some other courses. To put it in one sentence, character tables are really compendia of irreducible representations. In the discussion so far, we have encountered representations, right? What are representations? You need to tell me now. What is a representation? As far as symmetry is concerned, representation can mean other things. Yeah? Representation can define character? No, that is a very roundabout answer. I want a straightforward, simple, easy answer. Who will tell me? Yes? Excellent. A representation is a collection of matrices. Which matrices? No, one by one, transformation matrices. One dimensional or what, we will see that later. So, what we have done is we have used basis. What is the basis?
So, depending on like the set of coordinates or functions on which we set to operate.
Yes, basis is a set of functions on which the symmetry operations are performed. When we do that, we get a set of matrices. We get one matrix for every symmetry operation. The collection of the entire set of transformation matrices for a given basis is a representation. And as we saw, representations can be reducible. We had started working with XYZ for C2B, and we got a representation that was 3-dimensional. What is the meaning of dimensionality of the matrix? Sorry, I gave away the answer. The meaning of dimensionality of a representation is what is the dimensionality of the matrix. Okay? Each matrix in a particular representation, each transformation matrix has a particular dimension, same dimension, that is the dimensionality of the matrix. So, when you work with XYZ or with OHA HB for water, the dimensionality is 3. What we saw further is that when we worked with XYZ, the matrices were all diagonal. So, we could block factorize them conveniently to get 3 one-dimensional matrices. So, the initial 3-dimensional representation was a reducible representation. One-dimensional representation, of course, cannot be reducible. So, it is an irreducible representation. Next, we worked with the atoms of water, oxygen, hydrogen A, hydrogen B, and we got another 3-dimensional representation, right? Does that ring a bell? Was that reducible or was that irreducible? It was reducible, and it broke down into what kind of representations? How many representations? 2. So, one of them was one-dimensional, and that was a totally symmetric representation 1, 1, 1, 1, 1, and the other was 2-dimensional. Okay. Then we ended with the question, no, actually we ended with something else. Then we asked the question that we are using different bases and getting different representation. So, is that a good way of doing it? You keep on changing the basis, keep on getting representation, keep on trying to understand whether it's reducible or not, that cannot be a good method, right? Representations depend on the basis we choose. And then we don't even know whether the representation we got using HA and HB are actually reducible, whether that representation was actually reducible or was it an irreducible 2-dimensional representation. There is no way of knowing that. So, the way of knowing that is to use group theory, which we are not going to do here, but we have shown you the consequence of group theory. Consequence of using group theory to this problem is that we have this great orthogonality theorem, which essentially tells us that if you work with the matrix elements of irreducible representations, then they behave like orthonormal vectors. Are we clear up to this point? This is where we ended yesterday, I believe, right? We do not even have to remember this. What we will need to remember is the fallout of great orthogonality theorem, the 5 rules that come out of great orthogonality theorem. Today we are going to use them, and we are initially going to try and see whether we can work out the character table of C2V as usual. Okay. Before we start doing that, one more point. In C2V, when we had these characters of +1 and -1, what was the significance of that? What is the significance of +1? What is the significance of -1? What is the meaning of +1? What is the meaning of -1 character? Yes? Yeah, I heard some voice from here. Symmetric, antisymmetric, right? If the character is +1, then it is that basis element is symmetric with respect to that operation. If it is -1, then upon the symmetry operation it changes sign. So, for one dimensional representation is very straightforward. Okay? You perform a symmetry operation, any function that you take is either symmetric or antisymmetric if it is a one dimensional representation. Okay? So, +1 means no change, -1 means change in sign. As we will see, for representations of higher dimensionality, +1 and -1 can have some different meaning. Let us wait for that. Let me ask you another question. Is it possible that I have a one dimensional representation and the character is something other than +1 or -1? Remember the eigenvalue equation we wrote? R operates on some function phi to give you, now I will write chi as the eigenvalue multiplied by the same function phi. So, what we have seen is chi equal to +1 means symmetric, -1 means antisymmetric. My question is, can it be equal to 0? Can it be equal to 5? Let us start with 0. What would it mean if I had chi equal to 0, if I had character equal to 0? Why? Look at the eigenvalue equation. If chi is equal to 0, then what is the effect of the symmetry operation on this function? Annihilation is the word. Function vanishes, you are right, annihilation. So, a symmetry operation cannot be an annihilation operation, right? You perform a symmetry operation and the function dies, it is not even there because it is multiplied by 0. If that is the case, then there can be operations like that. Annihilation operator is used in quantum mechanics, but then that cannot be a symmetry operation. Okay? If the function vanishes, then where is the symmetry? Similarly, if the character is 5, then what does it mean? You have some function, some vector like this, you perform a symmetry operation, sign does direction does not change, the vector becomes 5 times longer. What is that? What is that called? What is this phenomenon? Something becoming longer or shorter? Yeah. So, I have a word for it. It is called distortion. It is distortion, right? So, a symmetry operation cannot lead to distortion. So, the point we are trying to make is that for one dimensional representations, chi has to be ±1 and nothing else. Is the point made? Right now, we are discussing only one dimensional representations. We are not talking about multidimensional representations as of now. Will you agree with me that for a one dimensional representation means what? It means that the functions do not mix with each other. Okay? So, any symmetry operation can either leave the function intact or at most it can change sign. If it say turns by some angle, then this vector cannot be represented by itself, it requires two components, then that means it cannot be one dimensional. Okay? Right. So, with this knowledge we can try to work out the character table, but before that let us take a look at the 5 rules. If you want, you can read up the derivation of these rules from Cotton's book. First rule actually is written at the bottom. I should have written at the top, but then I forgot, and then you can still read the bottom one first. First is, one of the questions we have asked so far is how many irreducible representations are there, and this is the answer. It can be derived using group theory. Number of irreducible representations, IR in this context means irreducible representation, is equal to number of classes. Okay, that is the first rule. Number of irreducible representation is equal to number of classes. How it comes, we are not deriving. Okay. In this course, we take it axiomatically, unfortunately. So, these are the 5 rules we need to know. Number of irreducible representations equal to number of classes. So, let us take our familiar example, C2V. What are the symmetry operations? E, C2, sigma V, we will write it as Zx, I will write this as Z, and sigma V dash, which is Yz. How many symmetry operations? 4. How many classes of symmetry operations? 4. Remember, what is the meaning of 2 symmetry operations belonging to one class? They should have the same action, or they should be interconvertible by some other symmetry operation. Okay. So, number of classes here is 4. On the other hand, if you want to talk about C3V, what are the symmetry operations? Ammonia, C3V, of course E is there, and C3 is there. How many C3 operations are there? 2, right. C3 plus and C3 minus, or C3 and C3 square, but they belong to the same class we discussed. So, they should have the same character. What we are trying to do here is that we are going to write a table with only the characters of the irreducible representations. Okay. So, I can write C3 and C3 square separately, but it does not make sense because the columns will be the same. So, I write it as 2C3. Have you understood what we are doing? It is absolutely okay if I write C3 and C3 square separately, but characters will all be the same, because what this translates as is that symmetry operations belonging to the same class have the same characters. This is something we have not proven, but demonstrated to you using I think plus and minus rotation by theta, right. Remember, sin theta, cos theta sin theta minus sin theta cos theta, and cos theta minus sin theta cos theta. Those were the 2 matrices. When we turned by theta, characters were the same. So, I just write them together. How many vertical planes are there? 3. Do they belong to the same class? Are they equivalent? Yes. So, again I will write as 3 sigma V, and do not forget I am writing it like this because they have same character. It is absolutely okay if I write sigma V A, sigma V B, sigma V C, but then they will have the same character. Okay. So, for here, what is the number of classes? What is the number of symmetry operations? 6. And what is the number of classes? 3. Let me write down this also. H is the order of the group, which is equal to number of symmetry operations, that is 6 here, and it is 4 here. Okay. So, in C2V, how many irreducible representations will be there? 4. For now, let me call them gamma 1, gamma 2, gamma 3, gamma 4. Later on, we will learn how to give them little more meaningful names. Right now, let us use like generic roll number kind of nomenclature, gamma 1, gamma 2, gamma 3, gamma 4. How many irreducible representations will be there in C3V? 6? 6 or 3? 6 or 3? 3 or 6? 3. So, make up your mind, you are oscillating between 3 and 6. 3? 3 is global minimum, we converge to that? Okay. So, gamma 1, gamma 2, gamma 3, all right. Now, let us so let me write one more thing a little axiomatically. The first row is always going to be this, no matter which character table it is, totally symmetric representation always exists. There will always be functions that are totally symmetric. So, the first row is always 1 1 1 1 1, okay. Now, what is the next rule? Second rule is sum over I, actually we have, it would be the third rule because we have already used up this one, isn't it? Sum over I Li square equal to H. What is Li? Yes, it is the dimensionality of the ith irreducible representation, okay. Now, here H equal to 4 and there are 1, 2, 3, 4. For example, if there is a horizontal plane of symmetry, okay, and Z is the principal axis of symmetry, will the character of Z be equal to 1 with respect to horizontal plane? No, right, it will be minus 1. So, Z does not always, Z is not always totally symmetric, okay. Right now forget the basis, we are, the entire purpose of this exercise is that we want to be able to figure out the irreducible representations without knowing the basis, okay. So, once we know the irreducible representations, we will try and fit the basis there, okay. And the answer to your question is no, Z is not always totally symmetric, it is never totally symmetric if there is a horizontal plane, all right, great. Now, 1, 2, 3, 4, 4 irreducible representation. So, I can write the dimensionalities as L1, L2, L3, L4. These are the dimensionalities of gamma 1, gamma 2, gamma 3 and gamma 4, okay. So, now if I use this rule here, sum over I Li square equal to H, what is L1 square plus L2 square plus L3 square plus L4 square? That is equal to 4, is that right? H equal to 4, 1, 2, 3, 4, understood? Total 4 symmetry operations, that is equal to H. So, L1 square plus L2 square plus L3 square plus L4 square, that will be equal to 4. Are we clear so far? Now, tell me what are the only possible values of L1, L2, L3 and L4? It has to be 1, 1, 1, 1, right? None of them can be 2, none of them can be minus 1, because dimensionality has to be a positive integer. So, what we learned right away is that for C2V, you can only have one dimensional representations, which means that the 2-dimensional representation that we had obtained using hydrogen atoms A and B, that is a reducible representation. It is not an irreducible representation. Are we clear? Okay. Now, if dimensionalities are all 1, then I hope you will allow me to write 1, 1 and 1 here. Why? Because character of the identity operation is always equal to the dimensionality of the irreducible, dimensionality of the representation. That is something we have discussed earlier. Are we okay with this? Right? Now, what more have we said? These are all one dimensional representations. So, the characters can only be +1 and -1, right? Do we agree? We said that about 10 minutes ago, right? +1 or -1. So, these 3 spaces have to be filled with +1s and -1. How many +1, how many -1, that we have to decide. To do that, come to this. What is this? This is the orthogonality condition, isn't it? Sum over R, chi I of R multiplied by chi j of R equal to 0, right. So, if I write one of these as say chi I of C2, chi I of sigma V, chi I of sigma V dash, then what does it mean? 1 multiplied by 1 plus 1 multiplied by chi I of C2 plus 1 multiplied by chi I of sigma V plus 1 multiplied by chi I of sigma V dash is equal to what? 0. Let me write it here then. We will just write here and then erase. So, maybe I will write here itself. So, I get 1 plus chi I C2 plus chi I sigma V plus chi I sigma V dash is equal to 0. Okay, 3 unknowns, 1 equation. Is it possible to solve this? In this case it is, because we also know that each of the unknowns can only be plus 1 or minus 1, right. So, now tell me how many plus 1s will be there, how many minus 1s will be there. There has to be 2 minus 1s and 1 plus 1, right. So, now what we can do is we can just fill in, it is like playing Sudoku. To start with, let us not forget these are all plus 1s, 1 plus 1 and 2 minus 1s, right. So, I will basically write all these 1s and play around with the minus signs. I will first put the minus signs here, then I will put say 1 minus sign here and 1 minus sign here, then I will put 1 minus sign here, 1 minus sign here. Your character table is ready. There will be 2 minus 1s and 1 plus 1. You can put in any order you want. I have put it in this order because I already know how I am going to name them. Okay. I already know the priority that we are going to follow for nomenclature, that is why I have written it that way. You could have done anything, alright. So, we stop here and we come back and talk about first of all how to name these, and we talk a little bit about 2-dimensional representations.